This video is about Lagrange multipliers, and I'm going to do two optimization problems. This is the first optimization problem. It says, find the volume of the largest rectangular box in the first octant with three faces in the coordinate planes and one vertex in the plane given by this equation. And there's another one down below, so I guess you could just fast forward if you want to see that one. And I should show it to you, but yeah, so there it is. It says find the point on this plane that's closest to the point 1, 2, 3. So those are the two problems that we're going to do, and we're going to use the method of Lagrange multipliers. And the idea here is that you can set up a system of equations, and the system of equations is given by gradient f equals lambda gradient g, where f is the objective function and g equals k gives the constraint equation. So just to, I guess, we're going to make everything concrete, so let's just get started with that. The objective function is the volume of a box. So the volume of a box is x, y, z. And the constraint on this problem is this. So, here, this is going to be f. This is the objective function, the thing that we want to optimize. And the constraint comes from x plus 2y plus 3z equals 6. So you can view this as being a level curve of a function g, so in this case k would be equal to 6. So this is saying that using partial derivatives we can set up a system of, in this case, 4 equations and 4 unknowns. So 3 of the equations come from this vector relationship between the gradients, and 1 of the equations is just the constraint equation. So let's write down what those are. So if I take the partial derivative of v with respect to x, I get yz. So yz is the first entry in the gradient of f, and so that's got to be equal to the first entry in the gradient of g, which is going to be lambda times the partial derivative of this with respect to x, which is just 1, so yz is equal to lambda. It's my first equation. Second equation is the second entry in the gradient of f, which is the partial derivative of this with respect to y, which is x times z. Now this has to be equal to the second entry here, which is going to be lambda times the partial derivative of this with respect to y, which is 2. The third equation is going to be the third entry of the gradient of f, which is the partial derivative of this with respect to z, which is x times y. And that must be equal to the third entry here, which is the partial derivative of this with respect to z. So that is lambda times 3. And I also have this itself as a fourth equation, and you can see that I have 4 equations and 4 unknowns, x, y, z, and lambda. I don't really care about solving for lambda, I just want to solve for x, y, z. Right. So I was thinking about drawing a picture. You should draw, all these, I hate not drawing pictures since I always tell people to do it. We could merrily proceed to solve this question with no picture whatsoever, but it can just, make the problem more satisfying to sort of know what's going on here. So it says find the volume of the largest rectangular box in the first octant with 3 faces in the coordinate planes and 1 vertex in the plane here. Okay, so you can read off from this equation describing the plane that the normal vector for this plane is 1, 2, 3. So you can kind of imagine that vector coming out of the origin, and I don't know exactly what it's going to look like, but it's going to make a plane which is going to be over the first octant, something like this. And so I'm graphing the plane by showing its intersections with the coordinate planes. And what we're going to be doing here is considering boxes. Sorry, my computer's about to die. boxes that have faces in the coordinate planes like this for two of their sides, and then this last corner comes from the fact that the constraint is that this last corner has to be inside the light green plane. So that's what the question is asking. That's its meaning. We could go ahead to solve it with the symbols without worrying about that, but that's what it actually means. So what can we do here? So y times z is going to be equal to, well, it's equal to lambda, and 2 lambdas are equal to x times z. So we could write that this means that this is equal to 1/2 of a xz. Right? Yeah, that's true. That's true. And okay, so this means that y is equal to a 1/2 x, and great, okay. So here, when I divided z out by both sides, I assumed that z equals 0 is not part of the solution, but you can just kind of see here that z equals 0 is not going to be a very good idea, because it's going to make the volume 0. So that's valid. And now, using sort of a similar strategy with these two equations, we can say that, what can we say? We can say that x times z is equal to, let's see, if we multiply this by 3/2, then we get 3 lambda. So we should say that 3/2 times xz is equal to 3 lambda, which is equal to xy. Okay. And for similar reasons, it's okay to divide out by x. And so you get 3/2. Z is equal to y, and I don't know why I put a little hat on z, he doesn't need one. So z is equal to 2/3 y. And we could just go ahead and express everything in terms of x. So this is going to be 1/3 x. Alright, so notice now that I know that y is 1/2 x and z is 1/3 x, and I have this equation which I can now write entirely in terms of x, and I can solve for x. So I can write down x plus 2 times 1/2 x. So that's just x, right? And now I can write plus 3 times 1/3 x is again just x. All this has to be equal to 6, and so what does that tell you? That tells you that x is equal to 2. Alright, so if x is equal to 2, then y is equal to 1, because y is 1/2 x, and z is equal to, good gracious, z is equal to 1/3 of 2, so that is 2/3, right? And so we can see that the optimal volume we can achieve for the box comes from the case in which x is 2, y is 1, and z is 2/3, and you can verify that these values satisfy this equation, so that means that they actually are on the plane, which is a check on our work. And if you multiply them together, you get the maximum possible volume is 4/3. Okay. So now we're going to do this problem, and right, so I'm going to set up the equations a little more quickly than I did in the first problem. So the thing that we want to maximize here is I guess we want to minimize it, right, is the square of the distance. So that's just the easiest thing to work with. So I want to write down the square of the distance between a generic point x, y, z and this point. So that's just x minus 1 squared plus y minus 2 squared plus z minus 3 squared. And so this is the objective function, and now this is the constraint equation. So let me write down my equations that come from Lagrange multipliers, and so they're going to be 2 times x minus 1 is equal to lambda, the partial derivative here is 1 with respect to x, and I get 2 times y minus 2 is equal to minus lambda, and I get 2 times z minus 3 is equal to lambda again. Okay, so now let's just do some solving. So this is saying that 2x minus 2 is equal to